So now let's take this is a dielectric material. Dielectric material has finite conductivity, right? So for dielectric material, so a special case that often arises that in your simulation domain you have metal, perfect metal, metallic waveguide, metallic aircraft, whatever, right? So that's what conductivity will be associated with it, infinity, right? So this is a dielectric material, a PEC, perfect electric conductor, sigma tends to infinity, right? Putting numerically something as infinity is a problem. So we need to work out the limit before we put it into the code, right? So what happens to this expression? Okay, divide by sigma. I mean, you will divide the numerator and denominator by sigma and take the limit. Correct. What will you get? Update equation E is equal to that is so at the position of the metal the electric field should be 0 as per the boundary conditions, but our update equation should also give me that. It should not be that the update equations are taking me in some different directions. So let's have a look at, so supposing I at some time instant I put the electric field equal to 0, let's say t is equal to 0, at start of my simulation I put it equal to 0, it had better remain 0, right, to respect physics. Let's see if that is happening over here. So what is the first term simplify to? Minus, yeah, right. So I will get E n is equal to minus E n minus 1 and that's it. The other term goes to 0, right. And so that, I mean, that's very helpful to me, because if I initialize it at 0 on a PEC, which is what it should be, it continues to be 0. I don't need to explicitly yeah, the update equation is automatically doing it for me, right. So in some sense what I am saying is that I don't need to explicitly keep running the update equations on the PEC locations. I can set it to 0. Either I can set it to 0 at each step explicitly, or I let the update equations run, they will keep it at 0. Okay. So if we initialize E to be 0 on the PEC boundary, it stays that way, right. So PEC, the PEC boundary condition is very trivially being satisfied. Okay. So what we have looked at is two very simple cases: dielectric material, plane, I mean without loss, and with loss we know what to do, we get an update equation, and PEC also very simple to do. Okay. So now let's actually ask, I mean what I was hinting at was that this equation over here, there is something wrong with it. Okay. So now let's go a little bit deeper into that. So we all know that most natural materials are dispersive, right. So there is a part of this which I am not going to be able to derive over here. It's I will give you a reference for it. So chapter 9 of Griffith's book on electrodynamics, right. Everyone has seen the blue cover book, right. So here he describes very properly how do you model the a dispersive medium using a simple spring and mass attached to it model. So what is the spring and what is the mass? It's for example an atom and the nucleus, and the electrons are modeled as the mass, right. So there is a positively charged nucleus, there is an electron, right, there is some spring constant between them. When the electromagnetic field falls on it, there is a polarization, there is a slight force that is exerted on this mass. So when you put all the force equations together and work through it, it's a very elegant derivation which shows you that the frequency dependence of refractive index, it comes out over there. So I'll recommend that you read through this, just a few pages of simple derivation. We'll start with the conclusion of that. Okay, the conclusion of this modeling, so what is a spring model? A spring models resonances. A spring is the most simplest model for a resonance. Okay, we've all studied this. For example, if a spring has no damping coefficient and if I excite it once, what happens? It just keeps going on forever, right? That's a resonance. Okay. So the interaction of an electromagnetic wave with a material is also, there are various resonances. For example, in your microwave oven, what is the principle? There is water molecules, it has a certain resonance. I send a EM wave at that frequency, and that resonance condition being met, it excites that resonance and heats up the whatever material is there. So after having done all of that, what do you get? Okay, so the convention is, so far we have been using symbols like D. We will say that this is the time domain picture, and if I want to talk about its Fourier transform, that is the spectral component, I will write it as d tilde. Okay, so this is the frequency domain. Okay. So as a conclusion of this discussion in Griffiths, what you get is that d tilde, so it has to be as a function of omega, okay, is actually epsilon r, epsilon naught is vacuum, right. So this relation that we have been blindly writing every time, that d is equal to epsilon e, strictly speaking is true, but in the frequency domain, not in the time domain. Okay. So that's I mean, because I am not showing you the derivation from Griffiths, it seems like where did this come from, but I mean, we will assume it for now. The moment you start dealing with realistic materials, this relation d is equal to epsilon e is incorrect to write in the time domain. The correct relation is only in the frequency domain. Okay. So this is just a fact, you will have to take it and go back and read this part. Okay. So now these are all, so this is in the frequency domain. Okay. So as a result of this, what is actually our time domain relation then? Convolution, right? This is a product in frequency domain, so in the time domain it's a convolution. So if I go over here to time domain, this will become d of t is equal to this epsilon naught will come out. The convolution will go from minus infinity to some t, right, same t over here. I have e of t minus tau epsilon r of tau d tau. Okay. The simple signals and systems. Well, we will keep it at t. What about, I mean, so for example, what about the fact that our material is a causal, this causality has to be respected, right? The d at a certain time should not depend on e at future time instants, obviously. So will any of these limits change? Right. So due to causality, this will becomes 0 due to causality. And for the same reason, we are going to limit our upper limit to t, right? Otherwise, this will e at future time instance will also come over here, right? So this is the true picture. So when we have naively been writing that dt is equal to epsilon e in time domain, what does it imply? What kind of epsilon satisfies that? So if d of t is equal to epsilon r t epsilon 0 e t, what is this value of epsilon r t? Is it, under what condition will I get this very simple relation? Look at the convolution relation. Rather, we are just writing it like this, right? We have been writing it like this, delta function, right? So then this convolution gives me this simple relation, right? So in other words, this is a material that reacts instantaneously to the incident radiation, because the response is, so you can look at this convolution as also the convolution of an impulse response with the input, right? And so if the impulse response is a delta function, that means the response is instantaneous, right? Which is unrealistic. No material can respond instantaneously to even a spring. Supposing you apply some force to it, it does not it does not instantly start oscillating. It takes some time. Similarly, when you remove the forcing function, it does not instantaneously stop. It goes for a while and then stops, right? So nothing is instantaneous in nature, right? So this is what we've been using all along, and we will now build a theory of what happens in realistic materials. Okay, this was not an issue at for our case of your integral equations, because there I was dealing with a single frequency. So I was anyway assuming e to the j omega t. So I was implicitly working in the frequency domain, and I was using this relation without really realizing it, and I was putting the value of epsilon at that frequency. So there was no problem there. The problem comes in now when I am explicitly in time domain. I have to worry about what is the relation of d and e in time, because our Maxwell's equations, the way in the differential form, they need time. Yeah. So this is let's assume that this is the main equation that we have to work with. Okay. So let's try to just think of what are the challenges that will come with trying to implement this equation in FDTD. Okay. So you remember your E cell, there is a update in time, there is a update in space, right? So there is E cell, time and space update. So for example, in this previous here, this equation over here, to calculate E n, how many past values of E do I need to store? Only one previous time instant and only one previous time instant of magnetic field. You do not see E0, E1, E2, E3 over here in this relation. So what does that tell you in terms of the memory requirements of my computation? I do not need to store the history of fields. I just need, if I wanted to for some plotting or something, then yes, but I do not need it to calculate future time instants, right? However, does this now tell you something else? Right. So if I were to just discretize this equation over here, tau is going from 0 to t. So if I want d at a certain time t, I need electric field not only at that time instant, but I need the entire history. Otherwise, how will I calculate d at that time instant? Right. So now I need full time history of electric field to get the displacement field.
So if you have some time, you need all of them before.
I need everything before. Otherwise, how will I calculate this integral? Right. So is that a problem? That's a huge problem, because this is needed not just, this is needed at every point on the E grid, not just at one point. You need it in all points of space. You need to store the entire electric field history for all time, right? So that's impractical. So just looking at this, you would just give up on FDTD, because it's not possible to store so much. You will only be able to run your simulation for so much time, and then you will run out of RAM, right? So So what do you do when you're faced with such a situation? As an engineer, what would you do? Reduce the number of the time history. Okay, that's one way of dealing with it. So you will face some approximation error. Anything else that you can deal with? Looks like a numerical? Numerical quadrature is a way of implementing this integral, but that's not going to help you. This integration is not challenging.
No, but then we can take the time or the limits there, right?
Yeah.
So we can take the.
Okay, so you can think of applying quadrature rule over here.
So we don't need to take all the time instead up to.
Yeah, but then that works, quadrature rule works when the polynomial or function that you're trying to integrate is well behaved, right? It will be accurate up to polynomial degree of so much, depending on how many points, and you don't know how jumpy this electric field is going to be. The error will keep increasing, right? For example, if electric field is a sine wave, how many polynomials do you need to represent a sine wave? Right, a very large amount, and finally it doesn't converge. So what we will do is we will assume a simplistic model rather than compromising on the calculation. We'll assume a simplistic model of this frequency dependence of permittivity and see if we can if that saves us from saving the entire time history. So our objective is to model a dispersive material realistically, at the same time not have to store the entire field history. If we can achieve these, then okay, then I can apply FDTD to dispersive materials. So the entire field of things like plasmonics and all, where they critically depends on frequency dependence of permittivity, needs us to be able to model this. Okay, right. So a very general model of this epsilon r as a function of frequency is what is discussed in this chapter 9. Okay, as a summation of various resonances. So after this class, please go back and have a look at it. What we'll do is we'll assume a simple version of that. Okay, and it's something which you all have studied. If you put epsilon r of tau equal to 0, but I mean the material, the field is always there. Epsilon r is telling you the response of the material to that field. You can't.
So if it's non-zero and only a specified.
It will not be non-zero anywhere, because as long as there is a field, this response is always going to be there. So it's not going to be 0. It's not in your hand. It's a nature's property. It's not in my hand. So the simplest model is actually something that you have seen. You have heard of Drude model. You've heard of Lorentzian models. You've heard of Debye models.